morning, this is Miss Billerbeck, and we are going to talk about 6.4 geometric sequence. A geometric sequence is a number sequence in which each term after the first term is found by multiplying the previous term by a common ratio. So what that means is if I have a numeric sequence 5, 15, 45, 35, it's a geometric sequence if it has a common ratio. If I put 15 over the first term, the term right in front of it, and then 45 over the term right in front of it, so 45 over 15, and 135 over the previous term 45, so 135 over 45, and they all have a common ratio of 3. So if they all equal the same common ratio, then you have a geometric sequence. So let's look at if we can determine if this is an arithmetic or a geometric sequence. So first we might say, well, the arithmetic sequence, we would look at a common difference. And that would be plus 1.2. And then from here, we have plus, let's see, that's 2.64. All right, so we already have a different difference. So this is not arithmetic. Difference, there we go. Difference. So that's different from those. So this is not arithmetic. So we've ruled that out, but it may not be geometric either. So we do need to see that if we have a common ratio. So we're going to put this term over 1. So we have a very good idea that the common ratio is going to be 2.2. So that should equal 4.84 divided by 2.2, and then that should equal 10.648 over 4.84, and then that should equal 23.4256 divided by 10.648. Now, if we knew this was a geometric ratio, we, of course, are not going to divide this one by this. We're going to go with this because we know that the common ratio would be 2.2. So what we're going to do is see, well, they all should be equal to 2.2. So let's take a look at what they are. So I'm using a calculator on this for expedience. So we are going to find that this one right here is 2.2. So that would lead me to believe that the others are 2.2. So we can estimate if I multiplied this by 2.2, I would get 4.8. If I multiplied this one by 2.2, I would get that. So since this all equals the same thing, this is a common ratio. So since it has a common ratio, it is a geometric sequence. All right, so let's take a look at this. We're going to start with our difference. So if we move from here to here, we have plus 74. And surprisingly enough, that's plus 74. Let's try again. Plus 74, and we're going to try again, plus 74. So they have a common difference. So if they have a common difference, this is an arithmetic sequence. Okay, so let's just rule out that this in no way is a geometric sequence. So if I did 75 over 1, that certainly does not equal 149 over 75. This is very close to 2, and this is very close to 75. Okay, so this is 70, well, this is 75, and it does not equal this, which is about 2. Okay, so it is not a geometric sequence. Okay, so it's good to know when we're looking at our data, what we're looking at, an arithmetic or a geometric sequence. Sometimes we might even run into other sequences like Fibonacci sequences or series. So Fibonacci is a very cool series. I saw that in your homework, so maybe I should talk about that briefly. So Fibonacci is you take, if you had 1, 1, 2, 3, 5, and then it just keeps going on. So this is 0 plus 1 gives you this term. 1 plus 1 gives you that term. This is 2 plus 3 is that term. Oh, sorry. 1 plus 2. There you go. It's officially, that's bad. But that 1 plus 2 is 3. There you go. See, we all make little mistakes. We just have to make sure we catch them. And then 2 plus 3 is 5. Okay, so this is called the Fibonacci sequence. It's a very important one, and apparently musical hits usually follow the Fibonacci, and also the Nautilus shell. Okay, so let's go on with this. So we have the recursive formula for a geometric sequence. So if we're looking at a geometric sequence, we see that AN equals R times AN minus 1. Now these are subscripts, so they're names, not exponents. Okay, so this means the nth term, and this means the term right in front of the nth term. So the previous term to the nth term. Okay, and R is our common ratio. Now we know this as B for our common ratio when we're dealing with exponential equations. But when we start dealing with sequences, we've changed that to an R. Okay, so the explicit formula for a geometric sequence is AN equals A1, which is first term, times the common ratio, and then our exponent is n minus 1. So that's n is the term number, and then we're going to subtract 1. And R, the common ratio, AN, is the nth term. Now, we might ponder this and realize, hey, that's very similar to this. Okay, so when we looked at this, this was the initial term. Okay, so this was term A0, okay, before the first term. And this is our common ratio, and this is X, so there's no minus 1. So we started with 0 right here. So let's go back to this one and take a look. So this one, if we start with the first term, what's 1 minus 1? It's 0. So basically it adjusts to be this similar to this formula. Okay, so geometric sequence will be an exponential expansion of data. All right, so let's take a look at this. Okay, so we want to write this data in a recursive formula. So recursive formula, we have AN, which is the nth term, equals R times AN n minus 1, and we should define what A1 is, so we have a reference point. So A1 is 3072. Now all we need to determine is what is the R, and then we have our equation. Okay, so R is going to be this term over this term, 768 over 3072. That should equal 192 over 768, and that should equal 48 over 192, which should equal 12 over 48. Not 12 over 48. We should say, hey, that's easy. That's 1 over 4. Okay, so if I multiply 48 by 4, I do get 192. If I multiply 192 by 4, I do get 768. If I multiply 768 by 4, I get 3072. So R is 1/4. So now we can write our final formula. AN equals 1/4 AN minus 1. Whoops, that's supposed to be a minus sign for the previous term. Okay, you can put little parentheses around that if that makes you feel better, but that's just a subscript that's all together. And believe it or not, it's just as easy as that. So if you ever see this little subscript on a test, you know you're dealing with a recursive formula because you don't use that subscript with the explicit formula. So we know A1 is this, and we know the explicit formula is AN equals A1 times R to the n minus 1. So we substitute that in for A1, we substitute 1/4 in for R, and we have our explicit formula. So we have 3072 times 1/4 to the n minus 1, and that's the equation. Now we use explicit when we do computer software programming because it's very efficient. Okay, and I'll expand on that in the next lesson, so next example, so you can see how tedious this one can be. So if you program with recursive, it's going to make the computer run slower because it has to churn through a lot of numbers before it can get to your answer, if the answer is maybe the 100th term. Okay, but explicit formula is very powerful. You can just go straight from here to the 12th term. So let's look at how we might do that. So a to the 12th equals 3072 times 1/4, and then we have 12 minus 1. So a to the 12th then equals 3072 times 1/4 to the 11th. Okay, so let's see what that is. So we have 3072 times, I'm going to put in 0.25 and then to the 11th. Okay, so that's going to give us a very small number of, now mine's in scientific notation, so sometimes computers will go into that. Let me actually write it out here. Okay, so if you have scientific notation on your calculator, it looks like this. And we use scientific notation so we can compare magnitudes versus the actual numbers. But if I were to look at this as a written out number, we would see we'd have several zeros. So I'd have 1, 2, 3, 7, 3. And so let me write that. Let's scoot this over a bit. Okay, so this is 7.32 times 10 to the -4th. Okay, so what that equals as a decimal without scientific notation is 0.000732. So scientific notation, it just wants to look at where all the numbers are and compare them. Because if you're using bacteria, that might be very small. You don't want to look at all these numbers in front of it. So one of the ways we find scientific notation is we count from the decimal 1, 2, 3, 4, and that's where the decimal is going to go. And then if it's very small, it's a negative exponent. If it's very big, like $1 million, that's 10 to the positive 6. So remember, $1 million is 10 to the $6, okay? All right, so that'll help you remember scientific notation. Okay, so let's go look at a real life issue or situation. It's not really a problem. Okay, so Leanna started her blog with 10 subscribers. Okay, so after a week, 10 people figured out, hey, this is a pretty good blog. Okay, so she's got 10 subscribers, and that's A1. Okay, her subscribers doubled each week. So now we know the common ratio is 2. How many subscribers will she have in week 9? So we have n equals 9. So we have some key data. So let's first do the recursive so you can see why we don't want to do this to a computer. So if we have A1 or A2, we have A1, we do R times A1. So 2 times A1, so that's 2 times 10, which is 20. Okay, A3 isn't going to be 2 times 20, which is 40. A4 is going to be 2 times 40, which is 80. A5 will be 2 times 80, which is 160. A6 equals 2 times 160 equals 320. A7 equals 2 times 320, which is 640. A8 ends up 2 times 640, which gives us 1280. And then A9, our goal is 2 times 1280, which gives us 2,560. Okay, so that's why we don't want to do that to a computer. It has to churn through all this stuff, and that takes time and memory, processing memory, and it makes your computer run slowly. So if we are going into programming, do not program with recursive. Okay, so let's do this with explicit. So we want the 9th term. Okay, so then we start with A1, which is A1 times R to the n minus 1. So that's a 9 there. And then that's 10 times 2, and then we're going to put 9 minus 1. So A9 then equals 10 times 2 to the 8th, and 2 to the 8th happens to be 256. And then when we multiply that by 10, we get 2,560, which is the same, okay? But we didn't have to do much. Okay, I broke this down into steps, but if you started off with this and put it in your calculator with little parentheses right here, you would be set. and you would have gotten 2,560. All right. One thing that I want to make sure that you understand is that when we are talking about terms, the difference from this and exponential again is we are talking about term 1 instead of term 0. So this is term 1, and this is term 2, and term 3, okay? When we were dealing with exponential functions, we started with term 0, okay? So that's why there's a difference in this formula with n minus 1, okay? So when you look at applying, whether you're going to apply an exponential function or a geometric sequence formula, remember geometric sequences number the terms 1, 2, 3, 4, not term 0, 1, 2, 3, 4. Okay. All right. That's it for lesson 6.3. Have a wonderful day. Bye.